Today we'll recap the key methods we've encountered so far in, for example, proving convergence of these iterative matrix methods. And then we'll move on to something called the condition number, which is a way of quantifying the stability of the AX equal B problem. Okay. Hello again. So what I want to do first is just do a recap of the key matrices concepts that we've come across so far. So matrices section, because I'm really conscious that this is probably, in terms of new material, this section has had a lot more new material than other sections so far in this module, and the next one will also have new material. So conscious that there's quite more to digest. So we were basically dealing with two problems. We had the inversion problem, so-called AX equals B, and we were dealing with those in related ways. We were dealing with those, first of all, we were looking at decomposing A into A equals L U decomposition, and just one slightly unhelpful thing, because we're using the same notation that's used elsewhere, but the L and U are lower triangular and upper triangular, but the key point about the L and the U in these ones is that they have non-zero diagonal elements, whereas the L and U we use with L plus U plus D have zero elements, which I've emphasized that's a number of places now throughout the last lectures. But so there's one way through was out just breaking down the matrix, and this is one of actually probably about 10 common decompositions out there, and we'll just sort of introduce you to one. And then we looked at the iterative methods, and we looked at the pair of Jacobi and Gauss-Seidel. And Jacobi was in the form of xm plus 1 equals c minus b of x of n. And it's all about iterating a vector by repeated multiplications of this B matrix as we go forward. And we also looked at L plus U plus D decomposition. And for example, we then inferred that B was this for Jacobi. So really these were defining the methods and also defining a way of deriving this B matrix from the A matrix. So if we decompose it in this way, and remember the L's here are slightly different from the L here, in that sense it has no diagonal, and the way to remember it always is that we've partitioned off the diagonal here. So that's just the way to remember it. And so the example here was the B matrix was here, so that we've got a recipe, if you like, from going from A matrix that you're trying to invert to this B matrix that you're multiplying through repeatedly for your Jacobi method. So those, then sticking with the iterative methods, we then analysed convergence of Jacobi. The first method we used was the so-called method. This is my terminology, by the way. There may be better terminology out there, but the essential method was the method of norms, and from that we had the key result that the norm, infinity norm of B less than 1 for convergence, and that implied that A must be strictly diagonally dominant. And the second method we looked at was the spectral method, where this thing called the spectral radius, S, is the maximum of the absolute values of the eigenvalues. And you need to have S less than 1 for convergence. Now for years this material has been going for a good number of years now in the maths department. We just looked at part 1, but given that these cases that are not covered by the method of norms, I thought it important to include the spectral method as well, and it's quite easy to compute and it's very useful practically. So those were the methods of convergence. Then finally, for a shorter bit, we also considered eigenvalue problems for large A. So that in that case, A VI equals lambda I VI is the equation we're interested in, and we solve this by taking powers of A, or repeated multiplication through by A. That's why I call it the so-called power method. And this method is used in the algorithm that ranks your web pages when you do a Google search every however long it is. Okay, so those are the key methods, and I would describe that as sort of really the core material on matrices. And the remaining 2 topics I want to look at are also important for your sort of fuller knowledge of the subject. The 2 topics I want to cover in the remainder of the matrices section is condition number and partial differential equations. The first thing is about understanding the stability of these matrix problems. We've assumed that these matrices we use are stable to small changes, but what if they're not? How do we quantify that? That's where the condition number comes in. So it's very important in practical computations to understand this concept. And then partial differential equations is where we're taking concepts from the second part of this module, the ODE section, if you like, and showing you and extending it to partial differential equations, and show that partial differential equations problems can be posed as matrix problems. So it's another example of where matrices come in practice. Okay, so I've got about 10 minutes to start on the condition number. So if we go to our inversion problem, how stable is AX equals B to small changes in X? We call that delta. I'm going to call that delta X, and B. E.g., one source of the small changes are round-off errors, yeah? So we saw in the ordinary differential equations bit of this module that small round-off errors can grow when a system is numerically unstable and corrupt the solution. In a similar way, we want to know with a matrix problem, what are the properties of A that mean it's insensitive to these changes or sensitive to it? Okay. So we consider small changes to x and b. So we're going to do x will go to x plus delta x, a small change in the x vector, and b will go to b plus delta b. All very straightforward. So we substitute those in, then our sort of like, if you like, perturbed or adjusted inversion problem is this. And that could be due to round off error in any of the quantities. It could be due to other things as well. And all we're going to do is subtract our original equation, ax equals b, and that then gives us an equation for the changes with a delta x equals delta b. Or, given our x is our solution, we're interested in perturbations to the solution. Delta x is a inverse. We don't have to explicitly calculate it, but it would be helpful to introduce the inverse here. So we're going to use the idea to understand this. So we're interested. So we're interested when small delta b causes a relatively big change in delta x. Let's write that at the beginning again. So we have delta x is the inverse of a and delta b. So you can have a little small round off error in b. Ideally you don't want it to affect the solution, but there's some properties in a that mean that it can. So if the eigen values of a are lambda I for all values of I, then the eigenvalues of the inverse are simply 1 over lambda I. And we used this already with the power method in the last result. So we're just using that as a given. You can have the eigenvalues. So the basically, when delta b is in directions of the largest eigenvectors of A inverse, with the largest eigen values of A inverse, and because it's 1 over lambda for the eigenvalues at A, and this is the smallest eigenvalues of A. So it's those smallest eigenvalues of A that when you inverse them are going to become the largest eigenvalues of the inverse, and they're going to have the biggest impact on the solution. Okay. So just to summarize, an error in delta B in B, delta B is amplified when 1 over lambda I is smallest. 1 over lambda is largest, and lambda I is smallest. So we begin to worry if we take all the, if we have a big, we're able to get all the eigenvalues out of a matrix, and it's got some really small ones there. We know that's maybe going to give us trouble in terms of the stability of the problem. Let me just keep an eye on the time. We've got 5 minutes. So let's now fold this into a number, which is going to be called the computational number, but now we've got the principles in place. So we know that delta x equals A inverse delta B. And we also know that x itself is also A inverse B. And we're going to write down some inequalities about the norms of these things. So we know that it's all about 1 over the eigenvalues with these inverses. So we can make a statement first about the modulus of x is greater than or equal to the modulus of b, and then we can actually, because we know there's a spectrum of eigenvalues and the eigenvalues are 1 over lambda, that the smallest value of modulus b multiplied a minus 1 modulus b is divided by lambda max. Okay, so what we've done is we've taken the modulus of a minus 1b, and because we know the eigenvalues, we can make it into an inequality, which is 1 over lambda max. So that's b, that's a. So we take the not the modulus, the norm of b, and then we'd also take the norm of a, the equation for the perturbation. So we had the modulus is the modulus of delta b, but again this is following the argument through before, that it's the minimum eigenvalue, the small eigenvalues that are going to give the biggest value in the perturbation. Sorry. Okay, so it goes the other way. The reason we're doing this first, this is really basically the argument we had before. Let's see if I can undo it. Okay, well, let me do it. So that's less than or equal to, which has been an inequality, delta b the lambda min. So the first one is due to the fact that we need, when we look at changes of delta x, we need to scale it, we need to do it relative to something, right? We can't say that delta x is large unless we do it relative to something. So we want to actually look at the modulus of the norm of the solution itself to scale the two things. So that's why we've written this first line as well, and it's using the same principles as we did before. And this second line then just encapsulates the argument I wrote down in words about 1 over lambda minimum. So if I call that C, D, and basically we're going to do D divided by C. So delta x divided by x normed, and so on and so forth, and we get delta x normed, but now as a fraction of the solution itself, so it has a meaningful value. Okay, not so meaningful if it's just on its own. And it's less than equal to then lambda max on lambda min, and then you have this again, the change in delta B relative to B itself. Okay, so that's actually a sort of a meaningful inequality now that we can buy by reasoning from eigenvalues. So I haven't gone through all the details about splitting things up into its eigenvalues. I've done that before in the other cases, and that's really not beyond the scope of this module. But I am using kind of the results we've used before with eigenvalues, that the eigenvalues of the inverse are 1 over lambda, and the eigenvalues of A are lambda. That's really the main idea. And we know, and the idea really we come out with is that the inverse is going to have its most effect when lambda is at its minimum, because it's 1 over lambda. But we need to scale that relative to something else to have a understanding of how it impacts on the whole matrix. So that's where the lambda max comes in, essentially. So from this inequality, we extract something called C, which is lambda max over lambda minimum, and it's called the condition number. And it's a very important number about this stability. Okay, I'm going to run out of time. So that's the key result, is that if you've got a matrix and you can get its eigenvalues and do the ratio of the maximum to the minimum, that's going to give a measure of the stability of the problem. Now, we need a worked example definitely for this, because it's been a little bit abstract, and but it's still such a useful concept, conditioning of matrices, that I want to keep it in this module, even though I don't consider it absolute core material. And I'll carry on with that next time.